Nice. Okay. So this says on the calendar, it'll say 11:59. That just means it's due that day. I didn't want to change the time. That's just the default setting. So know that you don't have until midnight to turn it in. You have until 11:15 or whatever, the 11:10 that's due that day. Okay. I do, like, if you did 6 of the 10 problems, you get 60%. So prorated how much you did. Okay. All right. Here we go. So we left with that example. Walked you through it. Okay. So I want you to think through all these. When is mechanical energy conserved? When is momentum conserved? When is a collision elastic or inelastic, and what's conserved there? And when is angular momentum conserved? I want you to think through those. The answers to those questions are really important. Yeah. I don't. They never gave me one. I can let you. Okay. Hopefully there are some, at least, aspects of this wrapped up in here. Mechanical energy is conserved if there are no non-conservative forces. Non-conservative forces doing work on the object or the system. Okay. So a non-conservative force. So a conservative force would be, give me some examples. Gravity. Oops. The two in mechanics is gravity and spring. If there is a potential energy, there's a conservative force associated with that. So like gravitational potential energy, elastic or spring potential energy. Okay. There's also like electric force is a conservative force. There's electric potential energy. Good with that? Okay. These two are what we're focusing on this semester. Okay. So everything else is a non-conservative force. If there's not a potential energy associated with it, it is a non-conservative force. Okay. So if there are no non-conservative forces doing work on the object, then mechanical energy is conserved. Okay. So, just mechanical energy is equal to kinetic energy plus potential energy. That quantity. Okay. So, momentum is conserved if there is or are no, was it are no external forces acting on objects in your system. If there are no external forces, if there are no unbalanced external forces acting on objects in your system. A lot of times in a textbook, you will see it written like this. The net external force is equal to 0. Okay. So, an elastic collision, we kind of think that as bouncy. Kinetic energy is conserved. On an elastic collision, kinetic energy is lost. On a perfectly inelastic collision, these stick together. All right, so I want to unpack that just a tad bit. Okay, so elastic collision does not exist in reality, maybe like at subatomic levels, but in reality, that's like saying a frictionless surface. But guess how often a frictionless surface occurs in physics problems? All the time. Okay, so they need to specify, though, that it's an elastic collision. Otherwise, you cannot assume that kinetic energy is conserved. Okay, any type of collision is going to cause, like, did Dr. Carlson take the two steel balls, clack them together, burn paper? Like, okay, get out a piece of paper. It's one that you don't care about. Okay. Yes, no. Okay. This, most people like characterize that as, oh, that's bouncy. Okay. Hold your paper up. Smell it. It's all right. You can smack anything you want. Oh, it is fun. Okay.
Good job, Joe.
So here's the deal.
How many pieces?
How many pieces can you go through? It's like 5 pieces.
Yeah.
So where did that? Okay, so what? That is evidence of thermal energy.
Which means the energy came out of that system into this.
Right. Kinetic energy was not conserved. It was lost due to heat, as evidence. You heard it. You're moving molecules. Energy was lost there. There's no such thing at a macro life, us experiencing stuff, as an elastic collision. This would be an inelastic collision. A perfectly inelastic collision is if one was clay and like stuck together. Good with that? Okay. And all those collisions, so long as you put those objects in your system, momentum is still conserved. Inelastic, elastic, perfectly inelastic, doesn't matter. Momentum is conserved. Kinetic energy is what is being held in question, what type of collision it is. Good with that? Okay. And angular momentum is the same thing as momentum. We just replace force with torque. Okay. So if there are no unbalanced unbalanced external torques acting on objects in the system. Okay. Those are pillars, big ideas that are going to direct how you're going to solve problems. You have to look at this at a scenario and say, okay, is momentum being conserved? Is mechanical energy being conserved? Is kinetic energy being conserved? Is angular momentum being conserved? Okay. All those are big picture ideas. That's going to okay, I'm going to go down this route. Because there's no longer, oh, we're talking about momentum chapter. We should use momentum. It's just mechanics. It's all fair game. Every question, you're like, oh, it could be mechanical energy. It could be, it might not conserve any of those, but at least it gives you a starting point. That's a good starting point. Okay? Good with that? So that's the facts. Applying that, that's the hard stuff. Okay? Good with that. Any questions on that? Okay. The AP test loves working energy. Like that is, for whatever reason, they are big on energy. Okay. So, and a lot of these equations are not on the equation sheet. Hopefully you get to use them enough that's you'll have those memorized anyway. But okay, so we dealt with forces a lot, and energy is also a big concept. So the question is, well, does force affect energy? Yeah, probably. Okay. Well, by how much? Can we quantify that? Can we give it a number? Can we measure that? How force affects energy? And that is why we came up with this idea of work. Work is the thing that connects force and energy. Okay, so just in general, we say force multiplied by the distance of that force is acting on it gives it work. This thing right here is the component of force that acts parallel to the direction of motion. Okay? And it's positive if the force is in the same direction as motion, and it's negative if it's in the opposite direction of motion. You're welcome. Let's see, how do we do that? Okay. Cell phones. Like anything, we'll say money, for example. It's a good tool. It can be used to do a lot of things. It can also be exploited. It can also corrupt people. It can also turn people evil. Okay?
Yes, phones, the origin of
So, like, not necessarily the origin of evil, but the tool that leads to disengagement of society can. We're going to use the cell phone as a tool. If you want to take a picture of that rather than writing all that down, I'm fine with that. I'm also going to post this PowerPoint. Okay. So,
close door. Turn the cameras off. So nobody knows.
shh. Okay. There's certain types of work associated with certain types of energy. Or I guess specific types. Okay, so network, that is the most general category. It's the work done by any and every force. It doesn't matter what type of force. We don't have to make a distinction. It's just all the forces acting on it. That's equal to the change in kinetic energy. Changes the motion. It doesn't matter if it's conservative or non-conservative. Now, as we go on further, we have some more specific things. The work done by a conservative force, that's equal to the negative change in potential energy. Okay, quick little demo here. Ready for this? Take a break from copying. Ready? Okay, just a timeout. When you are listening to a lecture, you have to know the difference, the balance between listening to what the person is presenting and frantically copying what's on the board. Okay? They can be a detriment to each other. Does that make sense? I will try really hard to give you ample opportunity, and I'll post this PowerPoint. Okay? So you'll have yeah, there's some value in listening. Okay, ready? If I am doing this, is gravity doing positive or negative work on this marker? Negative work. What's happening to gravitational potential energy? Increasing or decreasing? Increasing. As I lower this, is gravity doing positive or negative work? Positive. Gravitational potential energy increasing or decreasing? You see what the negative's there for. That makes sense? Okay. That's true with every conservative force related to its potential energy. Okay. If you have a non-conservative force doing work, so guess what? The law of conservation of energy said if there are no non-conservative forces doing work, well, what happens if mechanical energy is doing work? Well, then mechanical energy isn't conserved. Therefore, it changes. By how much, you may ask? Well, multiply that by the distance that is acting, and boom, that's your answer. That's how much mechanical energy is changed by. It is a huge class. I think I'm.
Oh, you got Katie. I want to teach Katie.
I want to take chemistry. You are correct.
All right. So, post this. All right, mechanical energy, kinetic plus potential. This is a these are the same way to write. There's just two different ways to tell the story. Okay, so these are very general. These work with any and every situation. The change in mechanical energy is equal to change in kinetic plus the change in potential. Bless you. If you wrote these changes final minus initial, and then brought everything over to get rid of all the negative signs, subtraction, you get this phrase here, or statement. Initial kinetic plus initial potential, that's your mechanical energy initial, plus the work done by non-conservative force. Well, that's like that. Okay, is equal to your final amount of kinetic energy. Either way you do it, it's totally fine. Okay, so, and then you have this idea of power. It's the rate at which work is done, either work divided by time or the change in energy divided by time. It's also equal to force times the velocity for an instantaneous value. Woo! Okay, on the equation sheet, they give you this, this, and this. Everything else, you gotta know how to make distinctions between the two. Okay, good there? Thumbs up when you're ready to roll. Okay. All right. So we saw this scenario yesterday. Okay, forget the, let's do this. All right, so question. Ooh, let me make a distinction here. And I am looking for a Y as well.
See it actually.
Yeah.
Is it a frictionless plane or is there?
Ooh, that's a good question. Let's do, yeah. Let's say the plane, inclined plane is frictionless. Yeah, you can, yeah, okay. Um,
It's frictionless. I miss
Well, that's why I was. Hey, which way is it going?
um, doesn't matter. Doesn't matter.
Is the Earth counted in the system?
Yeah, what's our system?
No,
Just for
It says the system.
just red and green.
Hey, maybe you never know.
What's our system? In that case, you still wouldn't be close.
Yeah, I don't think it's balanced.
Wait, so you don't.
Just for I don't know.
Okay. Okay, quick, just see where we're at. Thumbs up if you got this answered. Thumbs up if you got the first one answered. Thumbs up if you got the second one answered. Thumbs up. Third question. Fourth. Fifth. Okay, keep talking.
I think it's, yeah. Just in case. Let's
Please, this is not.
Well, you didn't mention. No. We're not changing it all. There's no change. Because angular momentum is mass times angular, and there's no angular velocity change. I mean, the angle is there's no angular velocity. Okay. Yes, I know. I don't know. It's not directed here. Yeah. Oh, I remember what she said. I mean, like, technically everything is no.
Okay, ready? Here we go. Mechanical of the red box conserved. No. Tension is doing work. Okay. I don't care which way it's going. It's doing work. Okay. Is mechanical energy of the system of the red and green box doing work? Sorry. Is mechanical energy conserved? Yes. Why? Because you could do it two different ways. The positive work done on one box equals the negative work done on the other. So they cancel each other out, because if your pulley is massless and frictionless, the force of tension are identical. And they're moving the same distance. You okay with that? Or you could consider this like the snake as one object. That tension is now inside the snake. You pull on my arm. We're not ever. I mean, you could if you wanted to. You're like a physical therapist, I guess. Draw a free body diagram of every bone in my body. It's just like, oh, I'm being pulled that way. Okay. The string becomes part of the snake. So the only external forces acting on it are gravity on the green and the X component of gravity on the red. You all right with that? Okay. Is momentum of the red box conserved? No. You got tons of external forces. Tension, gravity are all external forces. Okay. If you combined them in the system, still not. Gravity on both of those is still acting on it. Okay, and it's not being canceled out. Tension, like, yeah.
So when a system is accelerating, will it always not conserve momentum?
Yes. Yep. If it's just that system. If you're like, yes. Or you could say the center of mass of the system is accelerating. Another way to describe that. Okay. Like if you had to, like, the reason I like this better than that, if you had both objects experiencing acceleration this way, both objects would be experiencing acceleration, but the center of mass isn't. Does that make sense? Okay. Is the angular momentum of the red box conserved? Okay, this one, I'm just going to tell you this. I was curious what you'd do with this one. So what I'm going to say is this. You need to specify a point for angular momentum And okay, so angular momentum is I omega. This is for something spinning, like rotating, like rotisserie chicken, like what the Earth does in 24 hours. Okay. You can also say mass times velocity times the radius perpendicular. This is of a particle. Particle. Okay. This is like what the Earth does around the sun in a year. Okay. This one's easy because your axis of rotation is usually in the middle or somewhere inside the object. Okay. This is a little wackier because the axis of rotation is outside, definitely outside the object. Okay. You need to specify this. This would be more of a particle moving type thing. There's nothing like, the only thing spinning is the pulley, but that's massless, so it doesn't have any moment of inertia. Okay. So, but because this is right, I'm going to pick this. This is my point. This is my axis of rotation for both the red and the green. Okay. The pulley has a radius. And therefore, tension is, well, there's lots of forces. So there's a force of tension. That's exerting torque. Normal force, that's like that's like parallel to the radius. Well, no, that gets canceled out by the force of gravity, the y component of the force of gravity. And then this guy, that's also, let's see. Yeah, that's also exerting torque about this point here. So no, and the whole system, you could have that conversation. Also no. Okay. Big picture. That's kind of nitty gritty. The red. Let's say it's going down the ramp. It's doing this. Okay. So if you think of it rotationally, it's like doing that. It's speeding up its rotational speed. It's very big picture. That was like a junior high answer there. You're all right with that? Like it was speeding up about this point. So the angular momentum was not conserved. The reason why is because there's external torques from these forces about this pivot point. We'll get into that later. But, okay, this is the type of digging that you need to be used to. I'm not satisfied with, can you come up with a numeric answer? Okay, you see the level at which I'm pushing you to. Okay, how are we doing? Scale of 1 to 5, how are we doing on comfort zone? 5, rocking the socks. 0, like, why did I sign up for this course? Okay. This is review / I'm teaching you a different way to think. That's new. Okay? You've seen all this. I'm just like going deep. No calculus. This is all algebra. This is all stuff that you've seen before. We're just looking at all of these things for every situation. Okay? All right. So if the force is not constant, at this moment in time, the tools that you have to work with, you cannot just say force times time gives you change of momentum, impulse. you have to graph it and find the area under the graph, between the graph and the x-axis. Okay, and this is a vector quantity. So if you're above the x-axis is positive, below the x-axis is negative. Okay, force times distance also falls apart. You have to find the area of force times distance. Okay, kinematic equations out. Don't even touch them if your force is changing. Okay, special case scenario. You used them a lot last year. That's because we were nice to you. But the reality is forces are rarely constant. Okay. Good at that. How many more do we have here? Okay. Good. All right. This is a big picture. This is not just for physics. This is anytime you see a graph. Okay. Slope. Rise over run. Change in y over change in x. Mathematically, what are you doing to find a numeric answer for slope? You are hitting the what button on your calculator? Divide. You are dividing your y-axis by your x-axis. Okay? So anytime you see an equation that has a bar in it, a division, you can put whatever's in the numerator on your y-axis, whatever's on your denominator on your x-axis. You graph those, and it's going to give you what it's equal to. Okay? Or let's say you're given a graph. You're like, I don't know. What can I learn from this graph? Obviously, you can just read it and see what happens. But numerically, you can figure out, and I don't care what's on your x and y axis, if you divide those two, find the slope, it could tell you something. It might not, but it could tell you something. How do you know if it's relevant or not? In physics, what you do is you look at your units. Let's say you have newtons on your y-axis and seconds on your x-axis. Like, I don't know, what is that? What does that give me? Well, I've got newtons per second, and I'm going to go kilograms meter per second squared over seconds. So that's kilograms meter per second cubed. Yeah, I don't know any of that. I don't know. The rate at which the force is changing, I don't know. Yeah, okay. Sometimes it helps, sometimes it doesn't. Well, the area, to find the area, you are doing length times width. You are multiplying the x-axis and the y-axis. Finding the area. So, okay, newtons times seconds. Okay, so let's see what that does. Well, Newton times seconds. So I've got kilogram times meter per second squared times seconds. Let's see, that cancels. Kilograms, meters times seconds. Well, that's math. That's a lot. Oh, that's change in momentum. You can do that with any and every graph for the rest of your life. And you can come up with what this means, looking at the units of your x and y axis. That's a big STEM skill. Okay. So here's your progression. The slope of position versus time graph gives you velocity. The slope of velocity versus time graph gives you acceleration. If you multiply that by mass, you get force as a function of time. Okay. If you take the area under the graph, you get whenever you find the area, it's the change in this quantity, not the actual value, but the change in. The area of acceleration versus time graph gives you change in velocity. The area of a velocity versus time graph gives you change in position, displacement. Okay. Momentum versus time graph. The slope of that gives you force. Force versus time graph. The area of this gives you change in momentum. Work as a function of position. The slope of this gives you force. Force is a function of position. The area under that, gives you the change in these values. Good with that? Okay. Last thing, uniform circular motion is kind of a special case scenario. The force is always acting perpendicular to the direction of motion. How much work does centripetal force do? If it acts perpendicular to the direction of motion? 0. Centripetal force, whatever's playing the role, centripetal force will always do 0 work. Good factoid. Okay. This is not a force. Don't ever draw a free body diagram of something moving in a circle like this or like that, like death. Okay. Inertia is not a force. Okay. Good with that. Last thing, this is kind of goes without saying, we're pretty much there, but everything linearly has a rotational or angular counterpart. Okay. You've now been reviewed. Okay. We will start. I will stop talking and you will start doing stuff tomorrow. Okay. Yeah. And I'll post this PowerPoint on Canvas.